In this video, we're going to practice using our energy diagrams in the quantum mechanical model, and then we're going to use that information to draw an atom, kind of like a picture of an atom, using those quantum mechanics. So let's go ahead and get started. The atom that we're going to work with today is going to be nitrogen, which has an electron configuration of 1s2, 2s2, 2p3. And if you don't know how to do electron configuration, there's a video that I've done that describes how to do electron configuration, as well as making these energy diagrams from the electron configuration. So I'm going to do a quick example here of nitrogen. So if nitrogen starts off with 1s2, that's going to be the lowest energy orbital, and our orbitals are always described as dashes here, and I labeled it as the 1s. There's two electrons that are going to be in that orbital. One is going to spin up, the other one's going to spin down, and it's a filled orbital because each orbital can only have two electrons. And remember, if they're in the same orbital, they can't spin in the same direction. They have to spin in opposite directions. The 2s is the next orbital with a little bit more energy. Okay, actually, that's going to be the biggest gap. It's going to be between 1 and 2. And it has two electrons as well, so spin up and spin down. And then, just for review, okay, the p orbitals, okay, they're dumbbell shaped, but there's three orientations. There's going to be x, y, and z orientation for those p orbitals. So the p, every time you do a p block orbitals, there's always three of them. Okay, so 1, 2, 3, and we call those degenerate orbitals because they're the same energy. Now I have three electrons in there. So the first electron that comes in, it really can pick any one of these orbitals. It doesn't matter which one. Let's say it picks the middle one, okay? But if it spins up, then the other two have to spin up as well, and they're going to fill the unoccupied orbitals first. Kind of like kids on a school bus, okay? Everybody gets their own seat first, and then if we have to double up, then it happens when every single seat has already been filled up with at least one person, okay? So this is what we call an energy diagram, okay? And it kind of just shows our quantum mechanics, and it puts electrons in orbitals, which is different than the Bohr model. The Bohr model puts electrons in orbits that kind of, circle the nucleus, kind of like the solar system with the sun, okay? So we're going to use this information to make a drawing of a picture of a nitrogen atom. Now, as far as the nucleus is concerned, it's the same as a Bohr model. If we look at the numbers on the periodic table, 14 and 7 for nitrogen, that means that there's going to be 7 protons and 7 neutrons in its nucleus. Same thing that's true for the Bohr model is going to be true for our quantum mechanical model. Okay. Now, what becomes different is how we describe the electrons. And how are we describing, excuse me, sorry, still fighting a cold. How we describe these electrons is with the electron configuration in this energy diagram. So what we're saying is there's two electrons in what we call this 1s orbital. And there's a sheet that shows the pictures of each of these orbitals. Most chemistry classes really only make students memorize the s orbitals and the p orbitals. The s orbitals are going to be spheres, and the p orbitals, okay, are going to be dumbbell shaped. And I'll show you what those dumbbell shapes look like, but they were in that picture that I just held up to the camera a second ago. So let's start out with the 1s, okay? What this means is we're going to have a sphere that's relatively close to the nucleus. Now, because these electrons are waves, it's not like they have a path like the Bohr model does. They're basically going to show up, and then they're going to dematerialize, okay, because of their wave-like properties, okay? And then they're going to show up, and we don't know the path that they take from here to here. But after a while, if you kind of like time-lapse photography this, you're going to find out that these electrons have a high probability of popping up a certain distance from the nucleus, okay? But in all actuality, we don't know the path that the electron's going to take. So if we know its location, we do not know kind of like its velocity or momentum or kind of which direction the electron is going. and that's the Heisenberg uncertainty principle. Okay, so really we can have a lot of these locations, we have no idea where it's going, but after a while we get this shape of a sphere. Now it looks like a circle here because it's a cross section of the sphere. So I'm just going to label this as the 1s because it looks kind of like fuzzy and it's kind of hard to see. Okay, then we move to the 2s. Well, the s still means sphere, it's just further out from the nucleus. So the same thing's going to happen. It's going to pop up, we don't know where it's going. But after a while, you'll see another sphere that starts to take shape because all of these electrons have kind of like this distance from the nucleus that it starts to pop up at, okay? And we're going to go ahead and label that as the 2s, okay? Now the 2p is going to be this dumbbell shape. And the way the dumbbell kind of looks, it's kind of like two lobes and what we call a node, okay? And the node is in the center where there's a 0 probability of finding an electron. Some people call these tear-shaped. Our textbook calls them dumbbells. So if you can imagine me kind of pressing some weights here, as a dumbbell, that's the technical term that our author uses. But I think two lobes and a node is probably the most chemistry-friendly word that we can use. Okay, so I'm going to switch colors here. I'm going to switch over to kind of a green color here, and I'm going to do some lobes, okay, or some dumbbells. Now, there's 3 different orbitals here, okay? One is going to be oriented along the x-axis, the other one along the y-axis, and then the third one along the z-axis. So let's kind of work on that first x-axis one. So I'm trying to show this lobe popping up on the x-axis. Now, I kind of made it look like there was a path, but I'm not trying to do that at all. It's exactly the way we did the sphere. So it really should have been stuff like this, just kind of random. And then after a while, you see kind of this dumbbell that appears. You've got a lobe here and a lobe here. And we're going to label that as the 2px. Okay, so this is the 2p on the x-axis. Okay, and then I'm going to do the same thing on the y-axis here. I'm going to kind of get a lobe that comes up here and then a lobe that comes down here. But remember, I'm kind of like showing path there, and I'm not trying to do it. So a better way of doing it would be kind of more like this. Just keep doing this, just kind of random. We don't know where it's going to be next because we don't know the direction in which it's going if we know its location. But after a while, we get these lobes, okay, that pop up, okay, and I kind of got a dumbbell going this way, and we're going to label this as the 2py, okay? And I'm going to switch colors to do the z-axis. So if this is the x-axis and this is the y-axis, I've kind of made this difficult to draw on a two-dimensional board, but really the z-axis would be a lobe coming out of the board and a lobe going into the board. And I'm just going to try to do the best that I can do with this two-dimensional board and the way I've already set up my x and y axis. So this is kind of like coming out at you, okay? And then this is going back into the board, okay? But once again, it'd be more like kind of like this, just kind of all random until we get our 2p on the z-axis, okay? Now, if you want a better description of this, I have a model that would kind of like show the p orbitals, okay? So we'd have a dumbbell coming out this direction. That would be our x-axis. This would be our y-axis. And then a lobe coming out to you would be the z-axis, and going back into the board would be the z-axis. But this is 3 different orbitals. We got one orbital here on the x-axis, an orbital here on the y-axis, and then an orbital right through here through the z-axis. And this is kind of like what an atom looks like using quantum mechanics, okay? And as you can see, it looks really, really fuzzy. So I always ask my students, make sure you label, where is the 1s? Because I want to be able to see the 1s. Label the 2s so that I can kind of figure out where that 2s is. It's kind of hard to see with these other shells in here, but That's how you have to do it. If you add those labels, okay, and you do your fuzziness, like it works for me, okay. Now, as you can see, this quantum mechanical model is a really accurate description of kind of like what the atom looks like. But for us, it doesn't really help us a lot when we're trying to do things with it because it's so fuzzy. And that's why we typically will come back to the Bohr model, 7 protons, 7 neutrons, and we'll show it more like this, where we're showing like more particle-like behavior than the wave-like nature that the atom really has with its electrons. It's kind of easier to do bonding and other concepts because we can see the number of electrons on each of these shells, and we don't see that, okay, with the quantum mechanical model. But as far as a real picture of what an atom truly looks like, it's more like this than this. Okay, so this is easier to teach with, but this is more descriptive of what an atom really, really looks like. Okay, so if you found this information helpful or interesting, please make sure you like and subscribe so that the algorithm picks it up and gets it to more students that need help with chemistry.